good, so what's the last thing in our notes? I think if we. Phase space, right? And we did the phase space of the harmonic oscillator. So what we'll do now is a more general example. So, but I'll just put up the relevant points here. It's the set of these vectors, these two n component vectors. And this is interesting because Hamilton's equations can be written like that. The time derivative of that 2n component vector is a vector dh dq and minus dh dp, like that. Of course, the only one, by the way, this is not division, this is, the only one you can visualize is n equals 1, which is the one we did. But yeah, this is the motion of a point in phase space. So any point in phase space is an initial condition. And this differential equation, in fact, this vector field on the right side tells you where it's headed. So that's the idea. Then we do this for the harmonic oscillator, what we did last time. And we have the Hamiltonian, which is p squared over 2m plus k q squared over 2. And there, the canonical equations give you this. Time derivative of this vector is p over m and minus k q. And the phase portrait of this is for every energy, you've got an ellipse that's traversed in a clockwise orientation by the base point. So every energy, you've got these concentric ellipses. I'll do a third one. And you can solve this in the following way. You can say p squared over 2ne, I'm just going to write square root squared plus q squared over 2e over k. And of course, that's the equation of the ellipse. So yeah, the canonical equations give you this vector field, the right side, everywhere. That's the editor pulling across many arrows. And you can see what's going on with that thing right there. Okay, so here's our next task. Our next example, instead of the harmonic oscillator, we're going to do the pendulum. Okay? So it's going to be the ideal pendulum. And we're going to allow it to do 360 degrees. So this is one that can rotate fully. So our ideal pendulum here, I'm going to draw it like this. M, L, and phi. But think of it as being a rigid rod so that it can, do 360s. So yeah, it can go around like this, and we still have, it's hanging in normal gravitational potential energy. So what we need here is the Hamiltonian, and then we need an estimate of what's going on here, okay? And we're gonna see some similarities and some interesting differences. So yeah, that's our goal here, to do the Hamiltonian of the pendulum and then these phase diagrams. Yeah. So this is one, in fact, we can leave this picture up here. This is one where we'll take it from scratch again. Okay, so we've got our pendulum, and the first thing we want to get is the Lagrangian. And what do you guys think about the Lagrangian? We could use plane polar coordinates, but the length is going to be constant. In fact, let's just write things down like this. T is 1/2 m r dot squared plus r squared p dot squared. U is equal to mgy equals mg. I'll use 1 minus cos phi. Okay. And here, of course, we have r dot squared is 0, and r is equal to L. So now we can get our Lagrangian as being 1/2 m L squared b dot squared minus mg 1 minus cos phi. There's the Lagrangian. You've got so much more back there. Good, so what do you guys think? There's the Lagrangian. And by the way, if we were to do, well, we'll do this in a minute, but if we were to do small oscillations, what would we have to do here? So for small oscillations, we'd be near phi equals 0. Right, I'm measuring phi from the vertical, and we would do cos phi approximately 1 minus p squared over 2. That would take us right there. In fact, why don't we're gonna need this in a minute. Small oscillations, we could say 1/2 m L squared b dot squared minus 1/2 mg. Oh, there's an L missing in here. L. mg/L p squared over 2. That would be the small oscillations that we've discussed so many times. But we're not going there right away. So we would say that p sub phi EL e phi dot, which would be m L squared phi dot, and making that substitution here, H turns into m L squared over 2. We've got phi dot, we get p sub phi over m L squared plus mg Good. So now what's next? We could try to get that vector field. And it's going to be a little more difficult to solve. So next, we need phase curves for constant energy. Remember, H is the energy, so phase curves for constant energy, H T. And what they look like is a little more complicated, but we can do the following. First case is going to be for small feet. So we're just going to make use of what we just did right here. So for phi much less than 1, we have, I'll just write it down. I'm not going to write small, it is the small oscillations. I could put that there as well. P sub b squared over 2 ml squared plus mgl, well, let's do 1/2. This is what I had over there, plus 1/2 mgl b squared. Now, the thing is, this is the same as the simple harmonic oscillator with just a little renaming of letters. Instead of just 1/2, we have, 2, instead of a 2, we just have 2 ml squared. Instead of a 2m, we have 2 ml squared. Instead of a k, we have mgl, but we can just rename those. So what we see here is that, go ahead and label this phi and d sub phi. We still get our little concentric ellipses. But what happens say for a given, what happens for a small enough energy? Well, actually, let's increase the energy now. In fact, I'm gonna let you guys fill this in, okay, as a homework problem. We'll make this for starting for next week's homework, okay? So homework next week. What's gonna happen when the energy is sufficiently large, we're gonna have something like this. Here's what we want to do. We want to analyze this physically before we do it mathematically. And here's G. So what happens if I stand this thing on its head? I stand it on its head and I have perfect equilibrium and I let go. It just stays there, right? Ideal. So suppose I have it standing on its head and I give it a push. What's going to happen physically to an ideal pendulum?
Swings down.
It's going to swing down. What's it going to do when it gets to the bottom?
Keep going.
Keep going. It's going to make it all the way back to the top. In fact, depending on how much of a push I give it, it's going to have that same speed when it gets back to the top. So it's actually going to turn into a rotator. So the nature of the rotator is interesting, but the limiting case of just giving it an infinitesimal push is that it just comes back to where it started from. So if this here is standing on its head, that's a full angle pi. And if it goes to pi and then goes around again, it's gonna go to 3 pi. So we actually have to extend this by 2 pi, 3 pi. So if this thing rotates, this is a very special curve right here. And the phase diagram, by the way, let's give these the proper orientation. So here's the thing. If it has this initial condition up here, that means it has a positive angular momentum, right? It's gonna spin clockwise. And it's never gonna stop. You guys agree with that? It's gonna spin and never stop. So the phase diagram is going to look like this. It'll look like this. So this point really turns into an interesting one. So before we do this analytically, we want to just talk about it physically here. So this is the rotation. And the other rotation would be this one here. In that direction. So what's so special about this point here that I circled is the following. The origin, you go back to the origin here, this was a stable equilibrium, black dot here. It's a stable equilibrium, and the nature of a stable equilibrium is that it's circled by these concentric ellipses. This thing, when it was standing on its head, up here, is an unstable equilibrium. And the nature of the unstable equilibrium is that, look at the vector field here. So the unstable equilibrium has a completely different character in its vector field. This one, stable equilibrium, you have little circles circling it. This one here, you have these diverging arrows. And every other point in this phase diagram is essentially similar. In other words, you just have these straight lines here. Not straight, these wavy lines, but there's nothing fancy going on there. So there are these two crucial points, critical points, stable equilibrium, unstable equilibrium. So I'm going to write that down here as well. So this is the unstable equilibrium. And this is the stable equilibrium. And here's what our homework's going to be. We'll look at the Hamilton's equations in the area of the stable equilibrium, and we basically have them here, right? And we'll look at this Hamilton's equations around the unstable equilibrium, okay? And see if we can characterize the difference between the two. So let me write that down as a homework. So I'm going to erase this over here. I'll get this started in the following way. So let's call this homework. What we want to do is calculate the Hamilton equation stable. At phi, I'll just say phi equals pi, that one's good enough, okay, phi equals pi. Now the thing is, what's the energy? What's the energy? Let's write this Hamiltonian down again. We don't get lost here. We had p squared over 2ml squared plus mgl 1 minus cos phi. So around phi equals 0, what's the energy value? Around phi equals 0, what's the value of h in the equilibrium position? Any idea there?
Our potential energy is 0.
That's right, potential energy is 0. And if it's not moving, it's kinetic energy. Yeah, so it's also 0. So energy equals 0. Because it's not just enough to give the position, we have to know the momentum as well. So what's the energy at the equilibrium phi equals pi?
Sine pi is -1, right?
Yep, -1.
So we'd still have no momentum because we're not moving, but we have a lot of potential energy.
Yeah. So it would be mgl times 2. So the energy would be equal to 2 mgl. So yeah, when you calculate Hamilton's equations around stable equilibrium, you have to take into account what the value of energy is. And when I say around stable equilibrium, so not exactly on it, but around it, and then you want to get, so yeah, here I'll write equals pi with energy equals 2 mgl. So this is at the equilibrium, so around it you're going to have energy equals 0 plus some little delta E. Okay. And down here, you're going to have energy equals 2 mgl plus some little delta E. And what we're trying to do is characterize the vector field. Right? Hamilton's equations give us the vector field. So they characterize the vector field. At these 2 points, around these 2 points. So what you want to do is make sure you see this feature here. This is the one we talked about last time, so that's not hard to talk about. So the vector field at this one point, this is its character. It's just these concentric circulations. At this second point, out here at phi equals pi, what you're wanting to see is this. See how those are 2 different types of vector fields? You can even bring these into the context of some of your vector analysis concepts, because you've got a circulation here and you've got sources and sinks in this case. Okay, so So that's the nature of those two. Good, so we're gonna leave that right there. This is a good assignment for starting next week off. Let me get started on our new topic. Start bringing some demos in again. So yeah, this finishes up our discussion of Hamiltonian mechanics. We definitely want to have a good look at that assignment I gave on Wednesday, on Monday. With the electromagnetic Lagrangian and Hamiltonian. So we definitely want to have a good discussion of that, possibly on Friday. But our new topic is what's missing so far this semester. Rigid body motion. Who remembers anything about rigid body motion from Physics 4A? So yeah, I have a two-step version of this subject, in which what we do is we repeat the basic Physics 4A type of rigid body motion, and then we get into a much more technical version. But yeah, there's no point in doing a more technical version if we don't remember the basics.
Physics 4A, we worked with the center of mass last week.
Center of mass, that's good. What else?
I took Physics 4A like 2 years ago.
Yeah, okay. No, this is good. I'll bring some of the demos up as well that you may or may not have seen. But yeah, so rigid body motion, this is important. You want to start building satellites and other stuff, for instance. So this is our new chapter. We'll do a fair amount of good stuff on this one. So rigid body motion. And been able to set it up and remind ourselves of some of the concepts that we've seen before. Up until now, we've been doing what's called point mechanics. Even if I draw blocks and squares and what have you, it's always just a point because it's got one coordinate. Until now, we had point mechanics. So by the way, what are the conditions for me to call a block or a ball or something just a point? How can I just associate this thing with a single point in space?
Uniform mass density, symmetric shape, but I don't know.
Symmetric shape and uniform mass density is good. What if it's rotating? Then it's more than just a point. So you can't just have a point rotating. What you have to, so there are a couple things. To call it a point mass, you can say it's much, much smaller than any dimension of its trajectory. Or it's executing such a perfect one-dimensional motion that you can just focus on one point of it and associate that with the particle. So yeah, there were some requirements here for us to actually do point mechanics. But yeah, as soon as you've actually got something with real physical extent that's doing things like rotating, any kind of tumbling, then you have to take a lot more into account than that. Then suddenly you've got an infinite number of points in there. So up until now, point mechanics, I'll just check that off. So now we're going to talk about extended bodies. So extended body mechanics. And here's where we'll start bringing in the relevant concepts. And they were mentioned, one that was mentioned was the center of mass. That's very crucial. I already talked about the center of mass in terms of our point systems. They're, they have a center of mass as well. What other concept was germane? Anything coming to mind? Distant past. How about the moment of inertia? Remember that? Moment of inertia? We're going to develop all these things systematically. Moment of inertia. And what about some of the dynamic quantities, or the kinematic quantities, I should say? So when you have a rotating body, you need angles suddenly, you need angular velocity, angular acceleration. So angular, I'll just write angular velocity, etc. So yeah, for the dynamics, we're going to need mass distribution. For the kinematic aspect, angular velocity, and putting it all together, we'll repeat the ones we do in 4A, and then it's going to get interesting. It's going to get a lot more technical. So it's definitely worth repeating the concepts from Physics 4A. So let's even just get started. And we'll start with the basic rotational kinematics. Rotational kinematics. These really flow pretty well once you're reminded. And you can just consult whatever textbook you guys use back then. You'll have a chapter, whatever, you'll have rotational kinematics. And what we do is we start with angle, I'll call it theta. R and arc length S. So we define the angle. This is when we start using radians consistently. So degrees is pointless. So anyway, what we have here is S divided by R. And then we're going to let R be constant. And then we can do the change of angle with respect to time. We can call it theta dt. Now we're talking about circular motion, rotational kinematics and circular motion. So we just define that this way. We look up at the prior definition here. We have ds dt equals r d theta dt, or tangential speed here is equal to r times the angular velocity. Okay? So this is the angular velocity. So we've got angle, angular velocity, and we can construct alpha equals d omega dt equals d squared theta dt squared. And we can get, and let's write this down. So this is the tangential speed. When you're, this is the rotational motion side of the, Good. So this was, for our picture here, we're going around in a circle. And the construction of these three is entirely analogous to the linear case, the one-dimensional kinematics. So one, B kinematics, I'll put the rotation right here, and the linear over here, and here we've got theta, here we've got x. Here we've got omega equals d theta dt. Here we have v equals dx dt. Here we have alpha equals d omega dt. D squared theta dt squared. And over here we have a equals b dt equals d squared x dt squared. So this is nice, because we inherit a bunch of results that we've seen before. Namely, leave some space under that column here, but a equals constant. You guys know these kinematic formulas? Constant acceleration, you may remember you got x equals x0, v0 t plus a half, at squared, v equals v0 plus at, v squared equals v0 squared, 2a, x minus x0. These we've seen and worked with a lot. And what do we have over here in column B? We just invent them on the spot, right? By construction. So here, if we have alpha equals constant, what do we get for the first one here? How about you, Thomas? We just want this equation in the rotational quantities. Let's translate. Translate from Latin to Greek.
Now we can swap the x's with thetas.
Yep. We'll swap the x's with thetas. We swap the b's with.
Omega, I guess.
Got it. So omega naught t 0 plus 1/2 alpha t squared, and then ditto here, omega naught plus alpha t. So yeah, you can solve a bunch of, and then this one too is interesting. Omega squared, omega naught squared plus 2 alpha theta minus theta naught. So yeah, given certain conditions on a rotational problem, you can just easily answer any of those types of questions. Anything you can do with the linear case, you can do with the rotational case too. And what you do want to know is that you want to make use of this here. Say you want to relate how many turns you've taken to how far you've come. With a complete turn, you're rolling a wheel, for example, 2 pi radius, complete turn. But yeah, then you can get your complete angle here, and then you can get your distance, relate the distances as well. So yeah, in addition to this, we'll just relate those distance quantities. So I should add that somewhere to this chart. Yeah, this chart actually covers all manner of problems. So yeah, here in the middle, we would have distance Well, I can do it this way. Just S equals R theta, that does the trick. Make sure we're using theta in radians. And this is the one you need just to relate the linear quantities. And of course, you can relate the linear speeds and accelerations by these formulas as well. So in fact, I'll put them all in here just so that this is complete, and then we have equals. I'm gonna do lowercase, but R is equal to a constant right here. And, R omega tangential R alpha. So you notice we haven't related it to centripetal acceleration yet. That's not yet part of this, but it will be. It will be next. Good. This is what we're going to leave this for now. And Friday, we're mostly going to want to do those recitation problems. So I may not bring any demos. But we can start with demos next Monday. Put this all into context. Okay. Good. Let's leave it at that.